Integer properties. This is one of the test's favorite questions to ask about, the integer properties. So in this module, we'll be talking about all the properties of the integers. And of course, the integers are the non-fraction numbers. They include all the positive numbers, positive whole numbers, 1, 2, 3. They also include 0 and also negative whole numbers, -1, -2, -3, all that. That's the set of integers. And that's a good term to know, incidentally. The test will expect you to know what an integer is. In fact, most of what we'll discuss in this module concerns only the positive integers, the ordinary counting numbers, 1, 2, 3, 4, 5, 6, etc. So these are two specific categories of numbers we'll be focusing on in this module. Now, of course, the test includes all kinds of numbers other than this, but we're going to focus right now on these. In this particular video, we will discuss a few interrelated ideas. These are mathematical terms you definitely need to know and understand for the test. These are terms that will appear in test questions. So the big three to understand, first of all, are factor, divisor, and divisible. Let's start by discussing these terms with formulas and some simple numerical examples, and all these formulas assume that a, b, and c are positive integers. If we say that a times b equals c, so the product of a and b equals c, then we're saying that a and b are factors of c. In other words, we can multiply them together to get c. To say that a is a factor of c is to say that we can multiply a by some other integer, and the product will be equal to c. So, for example, 3 is a factor of 6. 25 is a factor of 100. Notice that 1 is a factor of every positive integer. That's an important idea. Notice also that every integer is a factor of itself. Thus, every positive integer greater than 1 has at least two factors, 1 and itself. So, for example, the number 84, whatever other factors it has, we know that one of the factors of 84 has to be 1, and one of the factors of 84 has to be 84. If c divided by a equals b, so in other words, we can perform this division and the output of the division is still an integer, then we say that a is a divisor of c because it divides evenly into c. One number divides evenly into another when the quotient is an integer. We can also say that c is divisible by a. Notice there is absolutely no difference between factor and divisor. These two words mean exactly the same thing. So we use one more in the context of multiplication, one more in the context of division, but really it means exactly the same thing. Every factor is a divisor, every divisor is a factor. Thus, we have three interchangeable ways to say the same thing, and the test will use all three of these. We could say 8 is a factor of 24, 8 is a divisor of 24, and 24 is divisible by 8. All three of those say exactly the same thing. They communicate exactly the same mathematical information. And so don't be confused. The test might use different wording in different questions. Similarly, 8 is not a factor of 12, 8 is not a divisor of 12, and 12 is not divisible by 8 because the quotient, 12 divided by 8, is not an integer. And what amounts to the same thing, there is no positive integer b such that the product, 8 times b, would exactly equal 12. This raises the interesting question, what happens when we divide 12 by 8? There are two separate but perfectly correct mathematical procedures. If two numbers divide evenly, then integer divided by integer equals integer. The quotient is an integer and that's it. That's very easy. But if the two items don't divide evenly, we have two possible options, each perfectly correct. Option number 1 is to have an integer quotient and an integer remainder. So there we would say 8 goes into 12 once, a quotient of 1 with a remainder of 4. Option number 2 would be to express the quotient as a fraction or decimal. So we could say 12 divided by 8, that fraction simplifies to 3 over 2. We could also write that as a mixed numeral, 1/2, and we could write that as 1.5. So both of these are perfectly correct. You will need to understand how to employ either option but you never will have to decide which one to use. The nature of the test question will always make clear which one of them they mean. In other words, whether they're going to be talking about remainders or whether they're going to be talking about fractions and decimals as a result of division. We discussed changing between fractions and decimals in the arithmetic and fraction module in the videos Conversion with Fractions and Decimals. So if that part is unclear to you, for example, if you haven't seen those videos, I would suggest go back and look at those videos. That's where we talk about how to turn a mixed number into an improper fraction, how to turn either into a decimal, that sort of thing. Later in this module, we will discuss remainders at a greater level of sophistication. So right now, that was just a taste. We actually have a later video that are going to be devoted exclusively to the idea of division with remainders. So that's coming up. Now on another topic, suppose we had to find all the positive factors of 36. Now a test question may ask, how many factors does 36 have? There are also procedures, for example, when we get to factoring quadratics, where it's going to be important to find the factors of a number. Also, when we find the prime factorization, it will help to find some factors of the number. But suppose we had to find all the factors. Well, it's certainly clear, for example, we know 1 is a factor, 36 is a factor. Maybe it's clear that 2, 3, and 4 are factors, 7 is not a factor. We could kind of go haphazardly, but there's actually a system we can follow to find every factor. The easiest way is to list the factor pairs, the pairs of numbers that have a product of 36. So the first pair I'm going to list is 1 and 36. Those are clearly two factors. 1 is a factor of every number. 36 has to be a factor of itself. Well, 2 goes into 36, so that would be 2 times 18. That gives me 2 more factors. 3 goes into 36. That would give me 3 times 12. 4 goes into 36. That would be 4 times 9. 5 does not go into 36, so we'll skip that. And then we get to 6, well, 6 times itself, so we stop with 6. Once you get to a number, if you get to a number times itself, or you pass and you reconnect with one of the numbers you have earlier on the list, something like that, then you know you're done. So now we know, we are guaranteed that we have found every single factor of 36. So we don't count 6 twice. Notice that 36 has 9 positive factors, including 1 in itself. And so the procedure, again, you just list them in pairs, you skip the numbers. If any number, the number is not divisible with that particular number, you just skip it, and then you keep going until either you double back on yourself or you come to a number that's the product of itself. For small numbers, numbers less than 100, we can count the positive factors simply by making a list of factor pairs. We will learn another more efficient technique for larger numbers later in this module. So for example, the test could give you a number like 12,600 and ask you to find how many factors does this have, and it would just take far too much time to list all those factors. It would take like 10 minutes to make a factor list. You wouldn't have time to do it on the test. Later on in this module, we'll actually talk about an incredibly efficient procedure, and we'll actually use that particular number, 12,600. We'll find the number of factors in it very easily. So don't worry about that now. Just know that for numbers less than 100, you can just make the list of factor pairs. Finally, a note about negative integers. I've been focusing mostly on positive integers here. Technically, it is true that both positive 4 and negative 4 are factors of negative 12. Both positive 4 and negative 4 are divisors of negative 12, and negative 12 is divisible by both positive 4 and negative 4. It's true that every positive factor, for example, 36 had 9 positive factors. We could just put a negative sign in front of them. There'd be 9 negative factors also. So usually we're not as concerned with the negative factors because they're just repeats of the positive factors, and that's why the test almost never asks about that or expects you to know it. But technically, factors and divisors could be negative, and that is something that we may have to watch out for on a more advanced question. In summary, we talked about the interrelated ideas of factors, divisors, and divisibility. We talked about options for division that don't come out even, remainders versus non-integer quotients. Remember, remainders we'll be discussing in much greater detail a few modules from now. We talked about listing the factors of a number by listing factor pairs and introduced the idea of counting factors. For larger numbers, we'll have another video later on where we'll talk about that in greater detail. And we talked about the seldom used rules for negative factors. Divisibility rules. So first of all, let's start up with a couple easy questions. Is 56 divisible by 7? Is 50 divisible by 13? Theoretically, those are questions you should be able to answer with little problem. The answer to the first, of course, is yes. 56 equals 7 times 8. The answer to the second, of course, is no. 13 does go into 52, but it does not go into 50. So first of all, I'll just mention, if these are not questions that you can answer just by looking at them, probably you need to practice your times tables a little bit more. You really need to have your basic times tables down so that questions like this are in fact very easy. Now a slightly harder question, is that long number divisible by 3? Well, no one expects you to do this division in your head. We can't do the full division and find the quotient, but we can use a divisibility rule to answer the question. And the test loves these divisibility rules. So first of all, divisibility by 2. Of course, all even numbers are divisible by 2. To tell whether a large number is even, all we have to do is look at the last digit. If the ones digit is even, then the number is even. So we have these large numbers. We can ignore the rest of the number and just look at the ones place. And in the ones place, we see 5, 1, 7, 3. Those are all odd, but the 6 is even. That means that the middle one, with a ones digit of 6, that's the only even number, the only number divisible by 2. So that's divisibility by 2. Divisibility by 5. This is another divisibility rule that involves looking at the last digit. If the last digit is a 5 or a 0, then the number is divisible by 5, otherwise it isn't. So again, we have big numbers like this. We could ignore the rest of the number and just look at that last digit. Indeed, we have a last digit of 5, so that number is divisible by 5, but the others do not end in 5 or 0, so they are not divisible by 5. So both of those rules, divisibility by 5 and divisibility by 2, those just involve looking at the ones place and nothing else. Now the rule for 4. This rule is similar. Here we look at the last two digits, the tens place and the ones place. So we have to look at two digits. If the last two digits form a two-digit number divisible by 4, then the entire number is divisible by 4. So again, our same list of long numbers. Look at those last two digits and think of them as two-digit numbers, 55, 41, 96, 37, 33. The only one among those that is divisible by 4 is 96. 96 is a number divisible by 4, so that means that that whole middle number is divisible by 4. Now divisibility for 3. The test loves this rule. This rule is a little different. Here we add up all the digits of the number. If the sum of the digits is divisible by 3, then the number is divisible by 3. And if the sum of the digits is not divisible by 3, the number is not divisible by 3. So, for example, with 135, we add 1 plus 3 plus 5, that's 9. Since 9 is divisible by 3, 135 must be divisible by 3. With 734, we add 7 plus 3 plus 4, that equals 14. Since 14 is not divisible by 3, we know that 734 is not divisible by 3. 1296, we add 1 plus 2 plus 9 plus 6, that equals 18. And since 18 is divisible by 3, then 1296 must be divisible by 3. So it works the same way for large numbers. Here's the question we had at the very beginning of the module. So is that large number divisible by 3? Well, here's what I notice. I notice that that middle 3 plus 3 plus 4, that equals 10. I can take the 5 plus 5, that equals 10. And that only leaves a 1, a 0, a 2, another 1, and those add up to 4. So that means that everything adds up to 24. The sum of the digits is 24, which is divisible by 3, so the original number must be divisible by 3. So all we have to do is add up the digits, and then see if that's divisible by 3, and then that tells us whether the number overall is divisible by 3. The divisibility rule for 9. This is exactly like the rule for 3. Add all the digits. If the sum of the digits is divisible by 9, then the number is divisible by 9. If the sum of the digits is not divisible by 9, then the number is not divisible by 9. So for example, 1296, we found on the last few slides that the sum of this was 18. The sum is divisible by 9, so 1296 must be divisible as well. 1372, we add these digits up, we get a sum of 12. So the sum of the digits is divisible by 3, but not 9. So the number is divisible by 3, but not 9. Notice, incidentally, 1372, the last two-digit number 72 is divisible by 4. So that's a number that would be divisible by 3 and by 4, which would mean it's divisible by 12. We can also use the divisibility rule for 9 for larger numbers. So is this large number divisible by 9? Well, we already found out that the sum of the digits is 24. So 24 is divisible by 3, but not by 9. So the original number, that 9-digit number, is divisible by 3, but not by 9. The divisibility rule for 6. Here we're going to have a combination. In order to be divisible by 6, a number must be A, divisible by 2, and B, divisible by 3. We check divisibility by 2 by looking at the last digit, making sure that it's even, and we check divisibility by 3 by finding the sum of the digits. So any even number divisible by 3 has to be divisible by 6. Is 1296 divisible by 6? Well, first of all, we know it's even. The sum of the digits we found already is 18, which is divisible by 3. Therefore, 1296 is divisible by 6. Is this long number divisible by 6? Well, clearly it's even. That's easy to determine. We add the digits, add the first 3, they add up to 15. The second 3 digits add up to 14. The last 3 digits add up to 17. 15 plus 17 plus 14 is 46. The sum of the digits is not divisible by 3, so the original number is not divisible by 3 or by 6. In this video, we discussed the most common divisibility rules, the rules for 2, 5, 4, 3, 9, and 6.
Multiples. The idea of multiples is actually pretty straightforward. The issue is that it's incredibly difficult and kind of frustrating to try to define what a multiple is in words. But if you understand the idea of multiplication, then you understand the idea of multiples. The biggest issue is that people tend to confuse multiples with factors. So, before we talk about any verbal definition, here's a nice, helpful visual definition of how multiples and factors are different. So let's take the number 12, for instance, right? Can you name a factor of 12? Well, how about 6 and 2? If I'm doing a factor tree here, right, and breaking it down into its prime factors. And then I can break 6 down further into 3 and 2, and there we go. I've reached the end of my factor tree. So 3, 2, 6, 1, and 12 are all factors of 12. Multiples just go in the other direction. So 12 times 2 is 24. 12 times 3 is 36. 12 times 4 is 48. So the way to keep your factors and multiples straight is remember that factors are below the line, this line that I've just drawn right here. Those are factors. And above the line are multiples. And as a mnemonic, right, multiply, multiples get bigger. So how many multiples does a number have? Well, an infinite number of multiples, right? I can keep multiplying 12 until the cows come home. But let's talk about an actual verbal definition. Now, just to preface this, the reason it's hard to put your finger on the verbal definition of a multiple is because it involves two numbers, right? So I could say something like this. I could say, if x is a multiple of y, then y is a factor of x. It's just the reverse. So, for instance, 36 is a multiple of 12. 12 is a factor of 36. You could also put it this way. If x is a multiple of y, then x is divisible by y. For instance, 36 is a multiple of 12, and 36 is divisible by 12. Finally, you could put it this way. A multiple of a number can be obtained by multiplying that number by an integer. So take 12 and then multiply it by 2. You have 24. Great. 24 is a multiple of 12. And again, my recommendation is don't worry about memorizing these verbal definitions. Just put it into that chart that we were just looking at. Okay, let's talk about the relationships between multiples of a certain number. If I add two multiples of a number together, the sum will itself be a multiple of that number. So for instance, 24 is a multiple of 12, right? 36 is also a multiple of 12. We have it right on the screen here, right? 36 and 24. And summed together, they make 60. Is 60 a multiple of 12? It sure is. So if I add two multiples together, the sum of those two multiples will itself be a multiple of that number. If I subtract two multiples of a number from each other, then the difference will itself be a multiple of that number. So, for instance, we take 48, which is a multiple of 12, right? And so is 24. And if I subtract 48 minus 24, I get 24, which is a multiple of 12. And then finally, if I multiply two multiples of a number together, the product will itself be a multiple of that number. So for instance, if I take the numbers 24 and 36, both of which are multiples of 12, I get 864. And you can check this on your calculator. Is that a multiple of 12? Well, is it divisible by 12? Then yes, it is. One note, this does not work for division. You can only do this for addition, subtraction, and multiplication. I'm just going to write that in. Not division. Let's do some practice on this. If 16x equals y, where x and y are integers, y must be a multiple of which of the following? And this is select all that apply. So there could be more than one correct answer here. Go ahead and put your video on pause, try this yourself, and then we'll talk about it. All right, so let's start out with this premise. If 16x equals y, then I can say that y is a multiple of 16, right? That's basically the definition of what multiples are. 16 times something equals y, so y is a multiple of 16. Unfortunately, I don't see 16 in this list here, so I can't pick it. But what I can do is break 16 down a little bit more. I could say, for instance, 2 times 8 times x equals y. Oh, well, 2 times this thing, whatever 8x equals, is y. Well, that fits my multiple definition perfectly, right? Y is now a multiple of 2. So A is one of the correct answers. And then I can just flip this around and say, well, couldn't I write 8 times 2 times x equals y? Well, sure. And then 8 times this unknown quantity equals y, so y is a multiple of 8. Can I go any further? Yeah, let's break 8 down. 4 times 2 times 2 times x equals y. So 4 times this whole unknown quantity right here is equal to y. Therefore, y is a multiple of 4. But I can't go any further than that, unfortunately, because if I break 4 down, it's only going to give me more 2's. And so the correct answers for this one are 2, 4, and 8. All right, a more difficult problem here. If k plus 200, and k plus 350 are multiples of p, then p could equal which of the following? you know the drill. Go ahead, put the video on pause, and then we'll talk about it together. Here's what I know. I know that some number, k, a bigger number, k plus 200, and then an even bigger number than that are all multiples of this smaller number, p. So if I wanted to, I could represent this in the same way that I've been doing before in this chart right here, right? P is the smallest number down here at the bottom, and p times something gets me k. That's what a multiple is. P times another something, or a different something, a bigger something, gives me k plus 200, and then p times the biggest of these three gives me k plus 350. What this problem is testing is your understanding of the multiple relationships. So if you need to go back and review that a few minutes ago in this video, feel free to do that. But remember, if I have two numbers that are both multiples of the same smaller number, then the difference between those multiples, the subtraction between those multiples, is also a multiple of that number. So let's take these two right here. I got k plus 200 and k. What's the difference between those two? Well, it's 200, right? So what does that mean? It means that 200 must be a multiple of p, because k plus 200 is a multiple of p, k is a multiple of p, so the difference between them must also be a multiple of p. Again, go back a few minutes if you need to refresh yourself on these multiple rules or multiple relationships. Okay, so 200 must be a multiple of p. What else? Well, what's the distance between k plus 350 and k plus 200? It's a distance of 150, right? I went 150 more to get there. So that means also, since k plus 350 is a multiple of p and k plus 200 is a multiple of p, that 150 must be a multiple of p. So whatever number I pick here has to be a factor of both of these two numbers. Or, put differently, both of these two numbers have to be a multiple of whatever number I pick. So let's run each of these numbers. Okay, is 200 a multiple of 20? Yeah, it is. Is 150 a multiple of 20? Nope, I don't think so. So that's out. Is 200 a multiple of 25? Well, 200 divided by 25 gives me 8. So yes. And is 150 a multiple of 25? Oh, yeah, it is. Look at that. So that one works for both of them. Let's double check the other ones. Is 200 a multiple of 75? Nope, it's not. And feel free to divide that in your calculator if you want to double check. Is 150 a multiple of 75? Well, it is, but it doesn't matter because 200 is not, right? How about 100? Is 200 a multiple of 100? Yes. Is 150? Nope, doesn't work. And finally, 150, well, 150 is a multiple of 150, but 200 is not a multiple of 150. And so our correct answer here has to be B.